Jack. This is our Signals and System final project. Today we're going to be exploring phase lock loop. I will be introducing the digital part of phase lock loop, and later my partner Mitch would be introducing the analog part of the phase lock loop. So what is a phase lock loop? Basically, there are three components to a phase lock loop. The first one is a phase detector. Second one is a loop filter, and the third part is a voltage-controlled oscillator. So, as we know that phase is an integral of frequency, a phase lock loop, the purpose of phase lock loop is actually to lock the frequency. As you lock the frequency is also locked. So the purpose of a phase lock loop is to match two signals' frequencies. So the input of the system, you have this signal that has a certain frequency, that's the input of the system. And then you detect the output of the system, and then you try to find a phase offset. That's what the phase detector is doing. So after you get the phase offset, you filter this phase offset so that it's a constant DC offset. And then you use that constant DC offset to drive the voltage-controlled oscillator. So as the voltage varies, the frequency output of this oscillator also changes. So the goal of the system is that in the end, your output frequency would match whatever your reference frequency is. And one little tweak about the system is that you can also have a divide by n here. So the n would be an integer here. So say it's divided by 2. That means that if your input reference signal is 1k, then it would somehow, the system would want to match these two frequencies. So this frequency in the end would be 1k. But since this is divided by 2, that means you would have a steady output of 2k here. So whatever integer you put in here, you can actually multiply the signal's frequency by that amount.
You could be a master, don't wait for luck. Dedicate yourself and you go find yourself.
There are two ways we can implement the phase detector digitally. One way is that we can take an XOR gate, which two inputs are the reference frequency, the reference signal, and the voltage VCO signal. In that case, you have a duty cycle, and then after the filter, you can have a constant voltage that drives the VCO. The second way we can implement the phase detector digitally is through two positive edge triggered D flip-flops. This setup would allow the system to detect which signal is leading the other and result in the speeding up or slowing down of the VCO signal.
So now I'm going to talk a little bit about phase lock loop in the analog domain. So we're going to have some sort of reference signal at a particular frequency and phase, and the output of the voltage-controlled oscillator is also going to be at some particular frequency and phase, but exactly 90 degrees offset. We're going to multiply those signals together and get out the product of those two, which after some math we see is one component that is at the sum of the frequencies and another component that is at the difference of those frequencies. But since those frequencies are roughly going to be the same, the component at the sum of the frequencies is 2f or 2 omega, and the difference of the frequencies is going to be roughly a DC offset, this sign of the phase error between the two. So, knowing this, we're going to stop thinking about this control system in terms of voltages and start thinking about it in terms of phase. This is an abstraction layer. So when we're multiplying the voltages, that is the same as saying that we're comparing the phases. So we'll compare the phases here. Then you have this sign of that phase difference. That's a nonlinear part of the thing. We'll filter out any high frequency components, so it is just this put it through the voltage controlled oscillator and get a phase estimate back out. Now because this is nonlinear, but those phases are very close to each other, we can say that that's roughly, or that's very close to 0, which means that we can take away the sign and simplify this system so that it is a linear system. And because it is a linear control closed loop system, we can describe it by this control function, which just describes any closed loop control system. And we can say that over time, this will tend toward a transfer function of 1, meaning that the input and the output are equal. Alright, so when you're comparing the output of the frequency generator to the output of the loop filter, then you get these two comparisons. The yellow is the function generator, and the blue is the loop filter. And you can see that as we change the frequency, that the output of the loop filter changes too. Okay, so we have here a demonstration of the voltage controlled oscillator. So as the output of the loop filter, which is the blue line, changes, then the VCO's output changes as well. I'm actually controlling the loop filter right now by changing the input frequency to the entire system, and you'll notice that as I go with the lower frequency here on the function generator, that the frequency of the 555 also decreases. So that is correct behavior. So this is comparing the output of our VCO, which is in yellow, to the input to the system, which is in blue. And you'll actually notice that right now they are tracking each other. They have the same frequency, and as I change the frequency, it's a very slight operating range, but as I change the frequency here, the frequency on the other one changes as well. And this is actually, yeah, that's like all I need to say, really.
And also, like, it's probably not very obvious on the oscilloscope, but the frequency changing range is actually operating, like, the range is like hundreds of hertz, right?
Yeah, a couple hundred hertz.
Yeah.